For 40 years, physicists waited. They believed a giant machine worth billions of dollars would confirm that one elegant, perfect theory to explain the universe. Supersymmetry. Everything was ready. But when the greatest experiment in history ran, we didn't find what we were looking for. We were completely wrong. The ring at CERN, instead of the predicted new particles, revealed flaws within the existing order. A particle wobbled in a way forbidden by the equations. A force behaved as no model had ever predicted. And the Higgs Boson, by remaining 10 million, billion times lighter than it should be, showed that nature had struck a balance, precise to 34 decimal places. But the real shock was that these anomalies might not be flaws at all. They could be a doorway to a new physics. But if you too are excited by the possibility that everything we know is about to be shaken to its core, then like this video and subscribe, because we are about to step through that door together. Let's begin. For decades, physicists thought they understood the fundamental rules of the universe. Because we had the Standard Model. It was an extraordinary theory, explaining almost everything known to science. So, they built the largest experiment in human history. Their goal was to find the final missing piece of this theory and declare victory. 175 meters underground. They built a giant machine. Their goal was to confirm what they already knew. But what they found was something else entirely. Hidden in the depths of the data was something the equations said shouldn't be there. A particle that wobbled in the wrong direction. A force that behaved in a way no model predicted. And everything changed. We now understand that the universe is almost entirely made of things we cannot see, cannot explain, and cannot account for. At the center of this story is a giant ring. It stretches for miles beneath the French-Swiss border. Deep underground, completely unknown to the millions of people living above it. This ring is the Large Hadron Collider, the most powerful particle accelerator ever built by humankind. Its tunnel is 27 kilometers long, carved out of solid rock over years of drilling. Because this machine has a single mission: to recreate the conditions at the beginning of the universe. On this colossal racetrack, protons travel in opposite directions. They reach a speed very close to the speed of light. To be exact, 99.9999991% of light speed. Because of this, Einstein's theory of special relativity kicks in. From the proton's own frame of reference, time for them nearly comes to a standstill, while for us on the outside, they complete 11,000 laps a second. For them, that lap takes less than a billionth of a second. This machine must be cooled with liquid helium to minus 271 degrees Celsius. That temperature is colder than the surface of Pluto. It's even colder than the cosmic microwave background radiation that fills intergalactic space. Because this extreme cold is an absolute necessity for the roughly 10,000 superconducting magnets that run the system. When two proton beams at this incredible speed and energy are collided head-on in one of 4 giant detectors, the resulting energy is focused into a space trillions of times smaller than a single cell. And in that moment, the first billionth of a second after the Big Bang is brought back to life. That is the true importance of this experiment. It opens a window to the birth of the universe. But the view from that window was far stranger than we expected. So, what did physicists expect to see? The answer lies in a theory known as the Standard Model. This theory is the product of about 50 years of work. It emerged in the late 1960s, when physicists were confronted with a confusing abundance of newly discovered particles. The theoretical efforts to bring order to this particle zoo created a remarkable framework. There's 12 fundamental particles that make up matter. 3 fundamental forces that carry interactions between these particles. And the Higgs mechanism, which gives mass to some particles. The Standard Model had achieved the highest level of precision a scientific theory could reach. For example, the anomalous magnetic moment of the electron has been both measured and calculated. The results agree with each other to 11 decimal places. This is a near absolute victory for a theory. So, scientists thought the LHC would find the last piece of this model and complete the picture. Finding the Higgs boson, the last particle predicted by the model, was the LHC's primary mission. But this victory would be the beginning of a much deeper crisis. As powerful as it was, the Standard Model was known to be incomplete because it didn't describe gravity in any way. It contained 19 free parameters that had to be measured or not derived from the theory. It predicted that neutrinos were massless, but experiments have since proven this to be wrong. It offered no explanation for what dark matter is. And most importantly, it couldn't explain why there is so much more matter than antimatter in the universe. These gaps were already known. The LHC was supposed to start filling these gaps. But, instead, it did something much stranger. On July 4th, 2012, CERN held a special seminar, broadcast live to the entire world. The spokespeople for the Atlas and CMS experiments presented the analysis results of the LHC collision data. Both experiments independently reported the observation of a new particle with a mass of about 125 gigaelectron volts. This matched the prediction for the Higgs boson. The final required particle of the Standard Model had been found. The theory was complete. Physicists celebrated, and they were right to celebrate. But just as those celebrations were happening, a problem that had been debated in theoretical circles for decades could no longer be postponed. The Higgs boson's mass of 125 gigaelectron volts created the most acute version of what physicists call the hierarchy problem. In quantum field theory, the physical mass of any particle includes contributions from virtual particle processes. These are quantum corrections arising from constant interaction with the quantum vacuum. For the Higgs boson, these corrections are huge, because these corrections are proportional to the square of the mass of the heaviest particle the Higgs interacts with, which is the top quark. Therefore, quantum corrections push the Higgs mass towards a value 10 quadrillion times larger than the measured 125 gigaelectron volts. For the Higgs to remain at 125 gigaelectron volts despite this enormous push, Bohr's very large positive and negative contributions must cancel each other out with a precision of 34 decimal places. This is mathematically possible. But it's like the universe balancing a pencil on its tip for 13.8 billion years. And there is no invisible hand holding the pencil. Something had to explain this cancellation. But nothing in the Standard Model explained it. This is the hierarchy problem. And for decades, there was one dominant solution to this problem, but an elegant idea that physicists had been waiting for decades. A theory almost everyone was sure was correct. According to this theory, every particle we know had a secret partner, and these partners were the cornerstones of an elegant theory called supersymmetry. The idea was incredibly stylish. It paired every particle we know with a partner of a different spin. Quarks had partners called squarks, leptons had sleptons, and the Higgs had a Higgsino. Because thanks to this symmetry, the huge quantum corrections that inflate the Higgs mass were automatically and perfectly cancelled out by contributions from these new partner particles. No fine-tuning was needed. Therefore, the physics community trusted this theory for 40 years. It solved the hierarchy problem. But there was more. The lightest supersymmetric particle was predicted to be stable and electrically neutral. This made it a perfect dark matter candidate. This theory solved the hierarchy problem, explained dark matter, and led to the unification of forces at high energies. Because of this miracle, almost everyone was certain that the LHC would find these particles. They were searched for at every accelerator, from LEP to the Tevatron, but none were found. Yet everyone pinned their hopes on the LHC because the LHC's energy should have been enough to reveal these hidden particles. But when Run 1 ended, no supersymmetric particles appeared. When Run 2 was completed with nearly double the collision energy, still nothing was found. The mass limits for gluinos, the supersymmetric partners of gluons, exceeded 2,000 gigaelectron volts. The limits for squarks passed 1,000 gigaelectron volts. Thousands of different analyses were performed. The result was always the same: nothing. The parameter space where supersymmetry could naturally solve the hierarchy problem was now largely excluded. This was the collapse of a 40-year paradigm. The greatest hope had turned into the greatest disappointment. The theoretical structure built by the brightest minds in the field had been demolished by the data. So, what would fill the void that supersymmetry was expected to fill? The answer came from an unexpected place, with a different shockwave. This was not an absence, but the presence of something being wrong. This shock came in April 2022 from a laboratory in the American Midwest. The subject was the W Boson. The mass of this fundamental particle, which carries the weak nuclear force, is predicted by the Standard Model with incredible precision. Because its mass is tied to a series of other precisely measured quantities, like the Z boson mass, the muon lifetime, and the virtual loops of the top quark and Higgs boson. All these inputs are known with high accuracy. Therefore, the mass predicted by the Standard Model for the W boson is 80,357 mega-electron volts. The CDF experiment at Fermilab had been working on its own measurement for over 20 years. From trillions of collisions, they selected about 4 million W boson candidate events. The result was published in April 2022. The measured mass was 80,433.5 mega-electron volts, 76 mega-electron volts heavier than the Standard Model prediction. This number may seem small, but the statistical significance of this deviation was 7 sigma. It's hard to grasp what this means. 7 sigma means the probability of this result being a statistical fluctuation is about 1 in a trillion. In the history of particle physics, a result published with 7 sigma has never turned out to be wrong. This is not a threshold that random noise can overcome. Either the CDF analysis contained the most complex analysis error in history, or the W boson was genuinely heavier than the standard model predicted, which meant the theory was fundamentally wrong. Both possibilities were extraordinary. But then the Atlas experiment published its own result. Their finding was consistent with the standard model. Two major experiments, contradicting each other. The physics world held its breath, while the W Boson debate occupied conference halls. Broadcast, a completely different anomaly, was making itself known. This was a measurement targeting how fast a particle spins in a magnetic field. And this anomaly persisted despite more than 2 decades of increasingly precise measurements. The particle's name is the muon. They are constantly produced when cosmic rays hit our atmosphere. Even right now, about 200 muons are passing through your body every second, silently, invisibly. The muon's magnetic moment is one of the most precisely known quantities in physics. Quantum mechanics predicts that this value should not be exactly 2, but should show a small deviation due to virtual particle processes. The standard model can calculate this deviation to 11 significant digits. The 17-ton superconducting magnet used to measure this value was first operated at Brookhaven. By 2004, the results showed a deviation of about 3 sigma from the standard model prediction. This was interesting, but not definitive. So, they decided to move the experiment to Fermilab near Chicago. The magnet was transported in one piece, Ortis on a barge, a journey that took 35 days. The improved experiment at Fermilab, with results published in 2023, increased the significance of the deviation to 5 sigma. 5 sigma is the gold standard for a discovery. This means the muon is interacting with something in its quantum environment that is not included in the standard model. This something was not directly observed. But lazarement, it was there, reliably, repeatably, inside the quantum foam surrounding the muon during its short 2.2 microsecond lifetime. The anomaly was real. So, a strange landscape emerged before us, the theory expected to solve the hierarchy problem. Supersymmetry was nowhere to be found. But at the same time, in 2 different experiments, 2 different fundamental particles were exhibiting behaviors the standard model should not allow. One particle was heavier than it should be. The other was wobbling differently than it should. Physicists no longer knew what to believe. The roadmap they had followed for years was torn up and thrown away. And now, all they had was a map of these strange anomalies, these mysterious clues within the data. This map could lead us to a new world beyond physics. But first, they needed to figure out what these clues really meant. Because the anomalies hidden in the data, these cracks, were only the beginning. When the truly shocking findings began to emerge from places we never expected, and when the truly shocking findings began to emerge from places we never expected, it became clear that these anomalies were just the start. While the world of theory was cracking, experimentalists were confronting realities in the depths of the data that defied the known laws of physics. Things that should not exist. These were no longer theoretical predictions. These were raw, baffling, and undeniable proofs coming from the machine itself. The first shock came from the LHCb experiment. The standard model has one of its most fundamental principles. It's called lepton universality. According to this principle, particles like electrons and muons should behave in exactly the same way except for their mass. This was supposed to be a law, but the LHCb data told a different story. They were studying specific B meson decays. The versions of these decays involving muons was supposed to occur at the same rate as the versions involving electrons. A value called ERK, this ratio, SH, was expected to be exactly 1. But Higgs, it wasn't. Measurements published from 2014 onwards consistently showed this ratio to be below 1. With each new data update, the statistical significance of the deviation increased. By 2021, the anomaly was approaching the 3 sigma level. This meant the probability of it being a coincidence was less than 1 in 1,000. This seemed impossible, because it implied the existence of an unknown new force or particle that distinguished between electrons and muons. Theoretical physicists published hundreds of papers. Exotic ideas like leptoquarks and Z-prime bosons were proposed. Could this be the first direct evidence of new physics beyond the standard model? Everyone held their breath. This felt like the beginning of the revolution that had been awaited for decades. But then everything suddenly collapsed. In March 2022, the LHCb team published a correction. The problem was in the model simulating how electrons behaved in the detector. The simulation had underestimated how often electrons emit photons. This had caused them to overestimate the electron detection efficiency. When this systematic effect was corrected, the RK ratio returned to 1. The anomaly had evaporated. Hopes for new physics were dashed in an instant. But within the same data, there was another ghost, and this ghost refused to leave. Another observable, known as P5', was being measured in the same B meson decay channel, and this quantity, since its first measurement in 2013, had shown a tension of about 3 sigma with standard model predictions. Even after the correction was made, this tension persisted. It had been there for over a decade. It could not be attributed to any systematic error. It was pointing somewhere. This stubborn anomaly was not as simple and clean as lepton universality, but it was more resilient. It was a quiet but persistent whisper that something was still wrong. And just as this confusion continued, another ghost appeared. This time, a ghost that revealed the psychological state of the field in December 2015. The LHC had just started running at its new record energy of 13 trillion electron volts, and then it came. A signal. An excess that could be the sign of a particle decaying into 2 photons, Sol, with a mass of about 750 gigaelectron volts. But that wasn't the real shock. The real shock was that this signal was seen in both the ATLAS and CMS experiments, independently, at the same mass. This was the kind of coincidence physicists are trained to notice. ATLAS reported a significance of 3.9 sigma, CMS 2.6 sigma. This had to be it, a new particle. The theoretical community practically exploded. 15 to 20 papers were being published per day. In less than a month, over 100 papers had been written. By August 2016, there were over 500 theoretical papers about a particle that hadn't even been confirmed to be real. Then, the updated results came, with 3 times more data, and the signal was gone. There was just a smooth background. It was a ghost, a statistical fluke where 2 independent experiments had a random upward fluctuation at the same mass. This event revealed just how desperate a field that had spent years searching for new physics and finding nothing had become. The threshold for excitement had dropped dangerously low. The very reason for the 5 sigma discovery standard was to prevent such missteps, a disappearing anomaly, a persistent anomaly, and a ghost particle. The data was telling a story, but it was not a coherent one. It showed just how challenging and misleading the hunt for particles can be. But what if what we're looking for isn't a particle? What if matter itself, in its most fundamental state, under the most extreme conditions, is rewriting all the known rules? Because when scientists looked into the very heart of the collisions, to where the most extreme temperature and density existed, they found something that connected the Large Hadron Collider to the mathematics of black holes. And this connection came from a place no one expected, from the most primordial state of matter. Because the LHC collides not just protons, quarks, but also heavy nuclei like lead. What emerges from these collisions is a state of matter that existed in the first moments of the universe. It's called the quark-gluon plasma, and this plasma exhibited properties that upended all known laws of physics. When two lead nuclei collide head-on at the LHC, the temperature momentarily exceeds 4 trillion degrees Celsius, 250,000 times hotter than the core of the Sun. At this extreme temperature, the strong nuclear force that holds protons and neutrons together is overcome. Quarks and gluons are set free, and they begin to flow as a plasma. Theorists expected this plasma to behave like a weakly interacting gas, because at this temperature, the strong force should have weakened. But the measurements showed the exact opposite. This plasma flowed not like a gas, but like a nearly perfect liquid. Its viscosity, or resistance to flow, was almost zero. This substance was the most perfect liquid ever measured, even more perfect than superfluid helium, cooled to within a few thousandths of a degree of absolute zero. But that wasn't the real shock. It was that the viscosity of this plasma was very close to a theoretical minimum value predicted by the mathematics of black holes in string theory. The math developed to study hypothetical black holes in 5-dimensional spacetime was describing the flow of hot matter in the world's most powerful accelerator with incredible accuracy. This was in no physicist's plan. It emerged from the data. The physics of one of the most mysterious objects in the macro world. Black holes, was explaining the collective behavior of the most fundamental particles in the micro world. How could this be possible? This was an unexpected and profound bridge, connecting two different ends of physics. But on the other side of the bridge, something even stranger awaited. This strangeness emerged in proton-proton collisions. The simplest system, not in heavy ions, in normal, ordinary proton collisions, but only in high multiplicity events that produce a large number of secondary particles. The CMS experiment discovered a strange correlation in these events called the ridge. This meant that two particles produced at very different locations were angularly correlated, as if they came from a common source. This was the defining signature of the collective flow seen in heavy ion collisions. It made sense there, because there was a plasma. But there was no mechanism to create a plasma state in proton-proton collisions. Two protons do not contain enough matter or energy to form a macroscopic liquid. Yet, the ridge was there. It was confirmed again and again in different years, at different collision energies. It couldn't be explained. It exhibited a collective behavior where particles moved together in a strange way. And it didn't stop there. The production of strange particles was also enhanced in these high multiplicity events. This was yet another signature of quark-gluon plasma formation. the Alice experiment found that this collective behavior showed a smooth evolution from the heaviest collision systems to the lightest. There was no sharp threshold. It was as if collective behavior was a universal property of high-density matter. The LHC had produced a measurement that exceeded the explanatory capacity of the best theories of matter. Even in the simplest collisions, something we don't understand was happening. While all these confusing findings were happening, the LHC was also systematically destroying another one of the greatest theoretical hopes, extra-spatial dimensions. These ideas, proposed to solve the hierarchy problem, should have produced dramatic signatures at the LHC: heavy graviton resonances, microscopic black holes. But the systematic absence of these signatures closed off another large portion of theoretical speculation. The Randall-Sundrum model predicted graviton resonances with masses of a few trillion electron volts. They should have appeared as a sharp peak in the mass spectrum of lepton pairs at the LHC. But Run 1 and Run 2 searched for these resonances and found nothing. The model's prediction that naturally solved the hierarchy problem was refuted by the data. Large extra-dimension models shared a similar fate. These models predicted deviations from the standard model in high-energy lepton pair production. Because virtual graviton exchange should have made an additional contribution to the process. But, again, no deviation was found, and perhaps the most dramatic search was for microscopic black holes. If extra dimensions exist, sufficiently high-energy collisions could create tiny black holes. These black holes would instantly evaporate via Hawking radiation, creating a giant shower of particles in the detector. This would be an explosive and unique signature that the standard model could not mimic. But it was never found. The absence of extra dimension signatures, charts, combined with the disappearance of supersymmetry, left the hierarchy problem completely unsolved. But this is the central truth of the LHC era. The machine was built with the expectation that one of the proposed solutions would emerge. But none of them did. The problem was real, but the solutions seemed to be wrong. So, what do all these discoveries, these anomalies, these ghosts, and these absences mean? The puzzle before us is like a jigsaw with pieces that don't fit together. On one side, the incredible success of the standard model. On the other, a series of stubborn facts that the model cannot explain, and sometimes even contradicts. To put the pieces of this puzzle together, we may need to question our most fundamental assumptions. Perhaps we need to understand more deeply how these pieces work. The technical details of the detectors and analyses, because inside this complex machine, how the data is collected and interpreted can be as important as the story itself. And in the depths of these technical details, so how does all this work? How are these anomalies, these ghosts, and these astonishing discoveries brought to light? Because behind these findings are incredibly complex and sensitive systems that push the limits of human intelligence and engineering. After the shocking speed of Part 2, let's slow down now. It's time to understand, to grasp how difficult it is to obtain these results. We need to dive into the technical details of the detectors and analyses, because to understand what an anomaly is, you first have to know how the normal is measured. The first mechanism is the LHCb detector itself, a specialized hunter, and you can think of it as a detective tasked with finding a specific person at a crowded party. General-purpose detectors like Atlas and CMS are giant cylinders designed to capture particles scattered in all directions after a collision. they take a picture of everyone at the party. But LHCb is different, because LHCb was built to study a special family of particles known as B mesons. These B mesons, produced in proton-proton collisions, travel at near the speed of light and tend to fly forward along the collision axis. Therefore, LHCb is not a cylinder, but a series of detectors looking in a single forward direction along the beam pipe. This allows it to be a sharpshooter. But that's not its true genius. B mesons have a very important property. They don't decay instantly, and after leaving the collision point, the primary vertex, they travel a few millimeters before decaying. This distance is small to the human eye, but for LHCb's silicon tracking detectors, it is enormous. These detectors can reconstruct a particle's path with micron-level precision. Therefore, when LHCb analyzes a B meson event, it finds the primary vertex where all particles came from. But then it looks for a second vertex, a displaced vertex, a few millimeters away from that point, where particles suddenly appear and transform into others. That is the fingerprint of a B meson decay. This technique allows LHCb to identify hundreds of millions of B meson events per year with incredible cleanliness, because it filters out the background noise that is a mess for other detectors, thanks to this displacement signature. This is why it can make sensitive measurements like lepton universality or P5'. New physics beyond the standard model often makes tiny contributions to these rare decays via virtual particles, and LHCb is specifically designed to listen with enough sensitivity to see these tiny effects. The second mechanism is a masterpiece of patience and control: the precise measurement of the W boson mass. You can think of it as trying to weigh a single grain of sand in the middle of a hurricane. The problem is not just finding the W boson, but measuring its mass with a precision of 1 part in a trillion. Because the standard model's prediction is that exact. The CDF collaboration at Fermilab worked on this task for over 20 years. They used data collected at the Tevatron accelerator at an energy of 1.96 trillion electron volts, from trillions of collisions. They selected about 4 million potential W boson events. But this was just the beginning. Measuring a particle's mass with such precision at a hadron collider involves incredible challenges. Because when a W boson is produced, a chassis, you measure the energy and momentum of its decay products. But these products can lose energy or be mismeasured as they pass through the detector. Therefore, you need to calibrate the response of every single part of the detector with extraordinary control. Furthermore, protons themselves are not simple objects. They contain quarks and gluons, partons, but in constant motion. The momentum distribution of these partons directly affects the kinematics. The motion of W boson production. You must model this effect accurately. The CDF team worked for years to control and reduce these systematic uncertainties. They cross-checked their results using multiple independent techniques. This was less a single measurement and more a work of art. Therefore, when they published their results in April 2022 and found a 7 sigma deviation from the standard model, the world was shocked. Because this was not a result that could be dismissed with a maybe there's a mistake. This was the result of 20 years of meticulous work, unprecedented analytical control, and the collective effort of hundreds of physicists. The power of this measurement came not from its statistical significance, but from the human effort and systematic control behind it. The third mechanism is based on a completely different philosophy: listening to the whispers of the quantum world. This is the technique behind the muon G2 experiment. You can liken it to watching a spinning top that is also moving along a circular path. The muon is a fundamental particle and has a spin, an intrinsic rotation. When placed in a magnetic field, this spin axis wobbles or precesses like a top. In classical physics, the G factor that determines this wobble speed is exactly 2. But when quantum mechanics comes into play, everything changes, because the muon is not alone even in empty space. It is constantly surrounded by virtual particle-antiparticle pairs called the quantum foam. These virtual particles momentarily change the muon's interaction with the magnetic field and shift the G factor to a value slightly different from 2. The standard model can calculate how large this deviation should be with incredible precision. The goal of the muon G2 experiment is to measure exactly that. To do this, they use a giant 17-ton, 15-meter diameter superconducting magnet. This magnet creates an incredibly homogeneous magnetic field. Muons are injected into this ring and stored for their short lifetime of about 2.2 microseconds. The genius of the experiment is that it measures 2 things simultaneously: the orbital speed of the muons around the ring and the precession speed of their spins. There is a very small difference between these 2 speeds, and this difference is directly related to the anomalous magnetic moment, G minus 2. If there is a yet undiscovered particle or force beyond the standard model that interacts with the muon, this virtual particle will also appear in the quantum foam and give an extra nudge to the muon's spin. This would create a discrepancy between the measured precession speed and the speed predicted by the standard model. The power of this technique comes from its indirectness. You don't have to produce the new particle directly. You just need to measure the tiny effect caused by its existence. This is an incredibly powerful method for probing new physics that might be too heavy for current accelerators to reach. And the 5 sigma result shows that this method has heard a whisper. As we've seen, these anomalies don't just appear by chance. Behind them are special detectors that track B mesons, while decades of precise mass analyses and ingenious experiments that listen to the deepest whispers of the quantum world. These experimental techniques form one half of the puzzle. But the other half is the theoretical calculations that allow us to interpret these measurements, because in both the P5 prime tension and the muon G2 anomaly, there is a shadow clouding the results, hadronic uncertainties. To deal with these uncertainties, physicists needed a completely different toolset, not hardware, but pure computational power. And this power would take them into a virtual universe, into the heart of supercomputers, into the heart of supercomputers. There, they developed a brand new method to solve the most stubborn problems of quantum chromodynamics, or QCD, because the biggest obstacle to understanding both the P5 prime tension in B physics and the muon EE2 anomaly are the hadronic uncertainties arising from the complex behavior of the strong nuclear force. The way to deal with these uncertainties is through a technique called lattice quantum chromodynamics. You can think of this technique as turning a piece of the universe into a computer simulation. But this is no ordinary simulation. It begins by dividing space-time into a 4-dimensional grid of points, lattice sites, and lines connecting them, links. Quarks live on these points. The gluons that hold them together move along the lines. In this virtual universe, the fundamental equations of QCD are solved numerically using massive supercomputers. This is the only way to calculate the non-perturbative effects of the strong force, or cadence those that cannot be calculated analytically. With pen and paper, in the theoretical prediction of muon G2, one of the largest uncertainties comes from the hadronic vacuum polarization contribution. This describes how virtual quark and gluon loops affect the muon's magnetic moment. Traditionally, this was estimated using data from electron-positron collisions. But this was an indirect measurement. Groups like the BMW collaboration used lattice QCD to calculate this contribution from first principles, from QCD's own equations, and their result, published in 2023, was significantly different from previous calculations. If the BMW calculation is correct, the standard model's prediction for muon G2 comes closer to the experimental value, and the anomaly shrinks. This started a major debate among theorists, because two different methods were giving different answers for the same physical quantity. The power of this technique is its ability to solve the problem from first principles. It is not an estimate, but a calculation from the fundamental theory. Therefore, as the power of supercomputers increases and algorithms improve, these uncertainties will decrease, and it will become clearer whether the anomalies are real or a theoretical misunderstanding. The second technique is the future itself, the high luminosity LHC. This is the next version of the current LHC, like the LHC on steroids, but you can liken it to a photographer upgrading their lens and sensor to collect more light. Luminosity is a measure of how many collisions an accelerator produces in a given time. Higher luminosity means more data, and more data means more precise measurements and a chance to see rarer events. The high luminosity ALHC staggering or HLLHC will use several ingenious engineering marvels to achieve this. First, new superconducting focusing magnets will be used to squeeze the proton beams even tighter at the collision points. This reduces the cross-sectional area of the beams, creating a higher probability of collision with the same number of protons. But one of the real innovations will be Crab cavities. Normally, proton bunches are longitudinal packets that collide head-on. But Crab cavities create electromagnetic fields that tilt these packets sideways just before collision. This way, the beams collide like a crab walking sideways, with maximum geometric overlap. When these two technologies are combined, the luminosity of the LHC will increase by a factor of 5 to 10 compared to the current ELHC. By the end of this program, scheduled to start around 2029, the total dataset will be about 10 times what has been collected to date. What does this mean? It means the Higgs Boson couplings will be measured with a precision at the percent level. It means any real anomaly currently at the 2 to 3 sigma level will be pushed to the 5 sigma discovery level, and it means any statistical fluctuation will completely disappear. The HLLHC is a filter of uncertainty. It will take every question the current data is whispering to us and shout back the answer. Because this machine is being designed to be the ultimate judge that will determine the future of physics. Finally, there is one of the unseen but most important fronts in this technical war, the precise characterization of the Higgs sector. Discovering the Higgs boson was one thing, but fully understanding what it is something else entirely. You can liken it to discovering a new musical instrument. First, you prove its existence, but Then you have to play it to understand how it sounds, what notes it can play, how it harmonizes with other instruments. This is exactly what physicists are doing. They are measuring how the Higgs couples to different particles, how strongly it interacts with them. These couplings in the standard model should be directly proportional to the particles' masses. So far, all measured couplings are compatible with the standard model at the 10 to 20% precision level. But this precision still leaves plenty of room for new physics to hide. For example, a new particle that changes the Higgs couplings by 5% would be undetectable with current data. But the HC's precision program will see it easily. The goal is to characterize the Higgs with the same rigor that the LEP experiment characterized the Z boson in the 1990s. At LEP, millions of Z bosons were studied, and these precise measurements constrained the masses of the top quark and Higgs boson before they were even discovered. Now, billions of Higgs bosons will be studied at the LHC and HLLHC, and the precision of these measurements will similarly constrain the masses and couplings of particles beyond the standard model. But the most challenging and perhaps most important measurement is to measure how the Higgs couples to itself, the Higgs self-coupling. This requires observing an incredibly rare process where two Higgs bosons are produced in a single collision. This process occurs only a few times in trillions of collisions in the standard model. This measurement directly tests the shape of the Higgs potential, the equation that determines the energy of the Higgs field. And this shape may hold clues to the origin of the matter, antimatter asymmetry in the early universe. These are the techniques. These patient, methodical, and incredibly complex processes that form the front lines of physics. On one side, the experiments that reveal anomalies. On the other, the theoretical calculations that allow us to interpret them. And the machines of the future that will take it all to the next level. This is not a moment of discovery, but a siege. We are slowly besieging the fortress of the unknown from all sides, with different weapons and different strategies. But the most exciting thing is that all these efforts, all these techniques, are leading us to one fundamental truth, to the biggest and most unsettling questions at the heart of this entire puzzle. Why are we here? Why is the universe not empty? And why is everything we see only a tiny fraction of what we should see? Because beyond these technical details lie the deepest secrets of the cosmos. And these secrets will carry us to the greatest climax in human history. Because hidden in the data are not just particles, but a reality. And that reality will carry us to the greatest climax in human history. Because hidden in the data are not just particles, but the answers to the most fundamental questions of the cosmos. Now the tempo goes to maximum. We are moving beyond the technical details. We're no longer talking about how, but what. Because in the shadow of all these anomalies, all these absences, lies a set of much larger, much deeper, and much more disturbing truths that shake the very foundation of everything we thought we knew about the universe itself. These are not the indirect findings of the LHC. These are the most shocking discoveries from the cosmos itself. On the grandest of scales, the first epic moment is the most fundamental question of existence. Why are we here? Why is the universe filled with matter? Why is it not completely empty? This is not a philosophical question. This is a concrete physics problem, and the standard model cannot solve it. It fails catastrophically. At the moment of the Big Bang, energy converted into matter and antimatter pairs. For every quark, an antiquark. For every electron, a positron. Because the laws of nature are symmetric. Therefore, as the universe expanded and cooled, these pairs should have completely annihilated each other. All that should be left is a sea of photons, nothing. But we are here. Everything we see, telescopes, planets, stars, galaxies, is made of matter, is 17 times heavier than the muon. But for quarks, the situation is even more extreme. While the up quark's mass is about 2 megaelectron volts, the top quark's mass is about 173,000 megaelectron volts. This means the top quark is 85,000 times heavier than the up quark. 85,000 times. They are both the same type of quark. They both interact with the same forces. But we don't know where this huge difference in their masses comes from. The Standard Model explains this by assigning different Higgs coupling constants. But this is not an explanation. This is just writing the observation into the equation. This mass hierarchy is one of the Standard Model's biggest failures, and at the heart of this mystery lie the particles that perhaps hold the biggest clue. Because neutrinos provided the first and only direct evidence that the Standard Model is incomplete. And their story is the greatest revolution in modern physics. Because neutrinos had something they shouldn't have: mass. For decades, neutrinos were considered massless in the Standard Model. This was a situation forced by the structure of the theory. But in 1998, the Super Kamiokande experiment in Japan changed everything. Super Kamiokande is a giant tank filled with 50,000 tons of pure water, buried a kilometer underground, and this tank was observing atmospheric neutrinos. Those created when cosmic rays strike the upper layers of the atmosphere. And they discovered something impossible. The number of muon neutrinos coming from below the Earth, passing through the entire planet, was significantly less than those coming from above. The neutrinos were disappearing during their journey. But they weren't actually disappearing. They were transforming. Muon neutrinos were turning into tau neutrinos. This process is called oscillation. And oscillation can only happen if the particles have mass. Massless particles cannot oscillate. This was one of the clearest and most shocking results in history. Neutrinos had mass. Therefore, the Standard Model was incomplete. It was that simple. This discovery earned Takaaki Kajita and Arthur MacDonald the 2015 Nobel Prize in Physics. It was the first and only direct experimental proof of physics beyond the Standard Model. But this revolution brought with it an even greater mystery. How do neutrinos get their mass? The most elegant explanation is known as the seesaw mechanism. According to this mechanism, the left-handed neutrinos we observe have incredibly heavy right-handed partners that do not interact with the Standard Model forces at all. And just like a seesaw, the heavier these right-handed partners are, the lighter the neutrinos we see become. This could explain why neutrinos are millions of times lighter than other particles. Because their secret partners may have unimaginable masses, perhaps close to the grand unified theory scale. And the most astonishing consequence of this mechanism is this: leptogenesis. According to this theory, the CP-violating decay of these heavy right-handed neutrinos in the first moments of the universe created an asymmetry between leptons and antileptons. This lepton asymmetry was then somehow converted into a baryon asymmetry. the excess of matter we know. If this is true, the reason for our existence is the incredibly heavy neutrinos we've never seen, which decayed in a trillionth of the first second of the universe. Neutrino physics has the potential to solve the matter-antimatter asymmetry problem. And this leads us to another ultimate quest: neutrinoless double beta decay. This is an incredibly rare nuclear decay that would prove the neutrino is its own antiparticle. This is a prerequisite for the leptogenesis theory to work. Experiments around the world are searching for this decay. The Kam-Lan-Zen experiment has set a limit on the half-life of this decay greater than 2 × 10⁻26 years. That is a quadrillion times longer than the age of the universe. But the search continues, because finding this decay could reveal not only the nature of neutrinos, but also the secret of why we exist. But amidst all these great cosmological mysteries and theoretical puzzles, there is another unsolved problem within the Standard Model itself. At the most fundamental level, a fine-tuning problem. But this one is far stranger and more unsettling than the Higgs hierarchy problem. It is known as the strong CP problem, quantum chromodynamics, or QCD. The theory describing the strong nuclear force is incredibly successful. But in its mathematical structure, it allows for a parameter called theta. This parameter can take any value between 0 and 2 pi, and this term causes the strong force to violate CP symmetry. If the value of theta were around 1, the neutron would have to have a measurable electric dipole moment, meaning there would be a separation between its positive and negative charge distributions. Experiments have measured the neutron's electric dipole moment with extraordinary precision, and they found nothing. The current best limit shows this moment is smaller than about 3 × 10⁻26 electron centimeters. The meaning of this measurement is this: the theta parameter must be smaller than 10⁻⁻10, smaller than 1 in 10 billion. So why must a parameter that can take any value between 0 and 6 be smaller than 1 in 10 billion? There is no reason for this in the Standard Model. This is even more impossible than a pencil balancing on its tip for 13.8 billion years. This is a wound at the heart of the theory. The most elegant solution was proposed in 1977 by Roberto Pache and Helen Quinn. They proposed a new symmetry that dynamically forces this parameter to 0. And the breaking of this symmetry requires the existence of a new, very light particle called the axion. The axion cleans up the strong CP problem. But the most remarkable feature of the axion is that it can also solve the dark matter problem. Axions produced in the early universe could form the cold dark matter that fills the universe today. 2 giant birds with 1 stone. This is an idea as compelling as the WIMP miracle, and the axion has not yet been experimentally ruled out. Experiments like CAST at CERN have searched for it and not found it. But new generation, much more sensitive experiments like AXO and ADMX are beginning to scan the parameter space where the theory makes its strongest predictions. Finding the axion would be one of the most important discoveries in physics. It would explain 2 great mysteries with one elegant solution. And this search is one of the most intensely pursued adventures right now. And then there is the most concrete and exciting hint about the future, coming from the LHC itself. In the Run 3 data that started in 2022, both ATLAS and CMS saw an excess of events decaying into a tau-lepton pair around 100 gigaelectronvolts. The local significance in each experiment is at the 2 to 3 sigma level. This could be a statistical fluctuation like the 750 giga-electron-volt ghost. But the fact that the same signal is seen by two independent detectors at the same mass in the same channel makes one pause and think. Because this mass region is theoretically very interesting. Many models like supersymmetry predict a second lighter Higgs boson in this mass range, in addition to the 125 giga-electron-volt Higgs. This excess is being watched carefully as the Run-3 data is analyzed. Will it grow into a discovery, or will it vanish like another ghost? We will find out in the next few years. But even this pales in comparison to the next step. The Future Circular Collider, or ETF-CC. This proposed machine at CERN will be 3 times larger than the LHCe. With a circumference of 91 kilometers, it will first operate as an electron-positron collider, measuring the properties of the Higgs boson with a precision below 1%. Then, the same tunnel will host a proton-proton collider with an energy of 100 trillion electron volts. This is about 8 times the energy of the LHC. This machine could directly produce new particles with masses of tens of trillions of electron volts, partially inaccessible to the LHC. Where do all these discoveries, wobble, these anomalies, these mysteries, and these quests lead us? They all point to a single conclusion. The Standard Model is the most successful approximate description in the history of science. But it is just an approximation, and the physics beyond it is the most important open question. These two facts are true at the same time, and neither cancels the other out. But now, after this dizzying pace, it's time to pause and think. Beyond all this data, these equations, these machines, what does this quest itself mean for us? What does our effort to penetrate this deepest layer of the cosmos tell us about who we are as a species? Because the answers to these questions lie not just in physics books, but also in the story of humanity itself, and the next chapter of this story. And the next chapter of this story is perhaps written not just in an equation or a data point, but in the reflection we see in the mirror. Because, after this dizzying speed, these epic discoveries, it is now time to pause and think beyond all this data, these machines, EOS, these theories. We must ask ourselves the most fundamental question. What is our place in this vast, all mysterious, and often incomprehensible cosmos? Because the deepest lesson that experiments like the LHC teach us is not just about the nature of particles, but also about the nature of the minds trying to understand those particles. This is the ultimate story of knowledge and ignorance, of greatness and smallness, of meaning and meaninglessness. The first and most overwhelming contrast is the contrast of scale. On one hand, you have the largest experiment in human history, a giant ring, 27 kilometers long, stretching 175 meters underground. Tens of thousands of scientists and engineers spent decades building it. It cost billions of dollars. But, on the other hand, is what this colossal machine studies: protons. A proton is about 1 femtometer in size, 1 quadrillionth of a meter. The LHC is a 27-kilometer microscope built to study a proton. This is a task more difficult than trying to see a single grain of sand from the top of Mount Everest. It's like trying to detect a virus at one end of the solar system from the other. How is it that we build one of the greatest engineering marvels in existence to understand one of the smallest things in existence? This disproportion reveals both the tragic and sublime nature of our endeavor. The tragic truth is this: we must confront how physically small and insignificant we are. The cosmos itself is an unimaginable void, 93 billion light-years across, and we are beings about 1.7 meters tall, living on a pale blue dot within this void. Our physical presence is less than a rounding error on the cosmic scale. The LHC is the most concrete proof of this fact, to see the most fundamental building blocks of the universe. We have to build a machine the size of a city. This is a painful reminder of how deeply nature hides its secrets from us. Our insignificance is directly proportional to the magnitude of our effort. It's like an ant trying to understand the ocean. It can never physically grasp the ocean. But here comes that magnificent but moment. Yes, we are physically like an ant, but our mind can grasp the ocean. We can never physically enter a proton. But, thanks to the data from the LHC, we can understand the quark and gluon dynamics inside it as if we were there. This is the greatest triumph of human consciousness. We are the part of the universe that has evolved to understand the universe itself. We are significant enough to realize our own insignificance. This means our greatest weakness is also our greatest strength. You are a part of this paradox. You are made of the same fundamental particles. Quarks and electrons, souls that this giant machine is trying to solve the secrets of. Every atom in your body was once forged inside a star, and now the brain made of those atoms is questioning the nature of stars and atoms. You are the universe's effort to know and understand itself. That's why this quest is not just a scientific curiosity, but an existential mission. The second contrast is the contrast of time. On one hand, there is a universe that is 13.8 billion years old. This is a duration the human mind cannot truly comprehend. The LHC tries to look back to the very beginning of this time, to the first billionth of a second after the Big Bang. We are trying to touch the beginning of time. On the other hand, there is our own fleeting existence. The average human lifespan is about 80 years. On the cosmic calendar, this is less than the blink of an eye. Science itself, in the modern sense, has only existed for a few hundred years. Particle physics is not even a century old. How can such temporary and momentary beings dare to understand something so eternal and without beginning? It's like a mayfly trying to understand geological time. The tragic side of this situation is our inevitable defeat against time. We are just a footnote in the story of the universe. Perhaps a word, a letter. We are a tiny wave in this vast ocean of time. The cosmos existed before us and will continue to exist after us. Our theories, our discoveries, our triumphs may be lost in this infinite flow. This is one of humanity's deepest fears, to be forgotten. The possibility that everything we do as a species, as a civilization, will turn to dust before the erosive power of time. This creates a deep sense of melancholy and humility. No matter how far we go, we will always be powerless against time itself. But, again, that but moment. Yes, we are temporary. But that fleeting moment, that priceless moment, is our moment. A mayfly cannot understand geological time. But we can. Our brain is a time machine that allows us to transcend time. Through the laws of mathematics and physics, we can recreate 13.8 billion years ago as if it happened yesterday. Within that brief moment, We can hold the entire history of the universe in our minds. This is our greatest victory against mortality. We cannot defeat time physically, but by understanding it, we can transcend it. You are a part of this fleeting moment. Your existence is that incredibly rare and precious window in the 13.8 billion year history of the universe where consciousness has emerged. You are not just a spectator. You are the way the universe remembers and records its own history. That's why every discovery is not just a piece of information, but a step towards immortality. Because this knowledge will live on after us. The third and perhaps most personal contrast is the contrast of loneliness and connection. On one hand, there is the unimaginable emptiness and silence of the cosmos. The nearest star system, Proxima Centauri, is 4.2 light-years away. This is a journey that would take tens of thousands of years, even with our fastest spacecraft. Galaxies are like desolate islands in a dark ocean, millions of light-years apart. This is a deep sense of cosmic loneliness. The question of whether we are alone in the universe is not just a scientific question, but a spiritual one. The possibility that we are the only beings in this vast emptiness searching for meaning is both terrifying and dizzying. This loneliness magnifies the importance of every anomaly, every mystery we find, because it's like a small candle we light against the darkness. The tragic side of this situation is our potential isolation. If we are truly alone in this cosmic ocean, then all meaning, all beauty, all knowledge exists with us on this small, fragile planet and could perish with us. This places an incredible responsibility on our shoulders. We might be the sole bearers of the universe's consciousness, and this consciousness could be instantly extinguished by an asteroid impact, a climate catastrophe, or a nuclear war of our own making. This is the sharpest knife edge of existence. To be alone is also to live with the risk of losing everything. The entire poetry of the universe might be written in our language, and when we fall silent, that poetry may be silenced forever. But within this deep loneliness, we find the most unexpected connection. Our connection to each other. The LHC is not the work of a single person or a single country. It is the product of the collective mind and labor of tens of thousands of scientists from dozens of countries, from hundreds of universities, people who speak different languages, come from different cultures, hold different beliefs, come together to solve the most fundamental secrets of the universe. This is humanity's greatest joint project. Unlike the physically distant galaxies, we are connected. Knowledge is an invisible network that unites us. You are a part of this network. By watching this documentary, by reading these words, you are participating in this global conversation. An anomaly discovered by a scientist at CERN sparks a curiosity in your mind. This is the most beautiful aspect of science. It transcends borders, languages, and distances. It reminds us that no matter how small and lonely we are individually, we can be incredibly powerful and connected collectively. Perhaps this is the greatest lesson the universe teaches us. We don't need to search for meaning in the stars. Meaning emerges when we look at each other, when we talk to each other, and when we try to understand together. Scale, time, loneliness. These great contrasts are just one part of the picture. Modern science presents to us. Each one leads to both humility and pride, while see both sadness and hope. But within this picture, another, perhaps more disturbing and transformative contrast, is hidden. This has to do with the nature of knowledge itself. That thin and constantly shifting line between what we know and what we don't. Because every new discovery not only brings an answer, but also gives birth to a dozen new questions. And in this process, we understand that our ignorance, is not actually a weakness, but the fuel for our greatest adventure. This is perhaps the most important contrast, that dynamic dance between knowledge and ignorance. On one hand, we have one of the most successful and precise theories in the history of science, the Standard Model, a set of equations that can predict the workings of the universe to 17 decimal places. This is the most concrete proof of how far the human mind can go, how fluently it can speak the language of nature. This is the power of what we know. But, on the other hand, surrounding this bright light is a much larger and deeper darkness, what we don't know. Dark matter, dark energy, the matter-antimatter asymmetry, the hierarchy problem, the strong C-P problem. Everything we think we know is just a small island in the vast ocean of what we don't know. How can we be beings who know so much and yet so little at the same time? The tragic side of this situation is that knowledge can be a mirage. Every new island of knowledge we see on the horizon may just be the beginning of an even larger ocean of ignorance. Every answer brings 10 new questions. We find the Higgs Boson, but it leads us to the hierarchy problem. We discover neutrino oscillation, but it throws us into the mystery of the origin of neutrino mass. This is a never-ending quest, as it's like the mythological story of Sisyphus. We struggle forever to push the boulder up the hill. But just as we reach the summit, the boulder rolls back down. This can create the feeling that we will never reach the ultimate limits of knowledge. There will always be more. There will always be another layer beyond our understanding. This can create an intellectual fatigue and even a sense of hopelessness. But it is at this very point that the true beauty of science emerges. Ignorance is not an end, but a beginning. It is not a void, but a potential. Every new question is an invitation to a new adventure. Sisyphus's boulder is not a punishment, but a purpose, because what's important is not reaching the top, but the act of climbing itself. The engine of science is not what we know, but what we don't know. Curiosity begins with the awareness of ignorance, and this curiosity is what drives us to build the LHC, to send telescopes into the depths of space, and to question the most fundamental secrets of the universe. It is to accept the fragility of knowledge, but still have the courage to seek it. You are inside this adventure too. Every piece of information you learned in school shows you what you know. But life itself teaches you how much you don't know. And instead of seeing this ignorance as a fear or a deficiency, you can see it as a playground. Every unanswered question is a continent waiting for you to discover. Even if you are not a scientist, you can carry this spirit of curiosity, because to understand is not just to know the answers, but the art of asking the right questions. The second and final contrast is a synthesis that perhaps brings them all together. That thin line between order and chaos. On one hand, there is the fact that the universe is built on incredible order and symmetry. The Standard Model itself is based on elegant mathematical symmetries like SU 3 times x SU 2 times U1. These symmetries determine how particles interact, which forces exist, and why the laws of nature are the same everywhere in the universe. This shows that the universe has a fundamental grammar. Everything operates according to a set of basic rules. This was what all physicists from Newton to Einstein, Koch, from Schrödinger to Feynman, were searching for: a simple and elegant order underlying the universe. And they found it. The tragic side of this order is how fragile and exceptional it is, because all these perfect symmetries are broken in the current state of the universe. The electroweak symmetry was broken by the Higgs mechanism, which gave mass to the W and Z bosons. Without this breaking, T atoms could not exist. CP symmetry is also broken, albeit by a very small amount, which may have created the matter-antimatter asymmetry. But these breakings are exceptions. The universe dances on a delicate balance between perfect order and seemingly random flaws that disrupt this order. It's like a single atom being in the wrong place in a perfect crystal structure. And this wrong atom, this symmetry breaking, allows for the existence of every complex structure we know, including life itself. This is a fundamental contradiction of the universe. Order is necessary for us to exist. But chaos, the breaking of this order, is necessary for us to be interesting. But the beauty of this contradiction is right here. Life blossoms at the intersection of order and chaos. The universe is neither a completely boring and predictable order, nor a completely meaningless randomness. It is a combination of the two. It is a game with rules, but it also has the potential to bend and break those rules. So are we. Human consciousness is a phenomenon that emerges from the deterministic, rule-based firing of neurons in our brain. But it also exhibits unpredictable features like free will and creativity. We are the most complex and beautiful reflection of this fundamental duality of the universe. You are a part of this dance. Your body stands on the incredible order of billions of cells working together. But your thoughts, your dreams, your emotions are fed by an unpredictable chaos that goes beyond this order. You are both symmetry and symmetry breaking, both law and exception. And this makes you both a part of the universe and its most unique expression. Scale, time, loneliness, ignorance, order, and chaos. This grand philosophical journey brings us back to where we started, to that ring, meters underground. But now we look at it with different eyes. We see it no longer just as a machine, but as a temple where humanity asks its deepest questions. It is our cosmic mirror. It shows us both how small we are and how big we can think, both how temporary we are and what permanent works we can leave behind, both how lonely we are and how much we need each other. As we approach the end of this journey, we now know that physics beyond the standard model is not just a scientific quest, but an effort to understand who we are. Every anomaly is not just a data discrepancy, but a secret the universe is whispering to us. Every new theory is not just a set of equations, but the audacity to push the limits of our imagination. The journey is hard and long. The answers don't come easy. But perhaps what matters is not the destination, but the journey itself. Perhaps meaning is hidden not in an answer, but in the questions we ask while searching for that answer. And now, with these final thoughts, it's time to bring everything together. What does the story of these particles, these forces, these mysteries, and these philosophical reflections ultimately tell us? Because the final act of this great cosmic drama, we've seen the world beyond the standard model. and the universe's greatest mysteries. But there's something I haven't told you. The most fundamental law of the universe might evaporate at the event horizon of a black hole. They say information can never be destroyed, but black holes devour it. Stephen Hawking thought he solved this mystery, but he actually started a much bigger war, the information paradox. On our next journey, we will question the ultimate fate of information. Are you ready?